Welcome to Maths with EJD. In this video, I'll be starting with sequences and series. So let's see how far we go on this particular journey. This is a very important topic in maths, and even in real life, we have a lot of sequences happening in life, in music, in finance, in different areas like that. So let's go straight up and talk about what a sequence is. Okay. So a sequence is a is an ordered list of numbers. Is an ordered list of numbers. So ordered is really important. It's an ordered list of numbers where each number each number is called a term. Each number is called a term. Okay. Then sequences can either sequences can either be finite. Okay. By that we mean it has a specific number of terms. So with a specific number of terms. Okay. So sequences can be finite with a specific number of terms, or they can be infinite. Sequences can be infinite, and that means they continue indefinitely. They continue indefinitely. Okay. So that's like a kind of what is a sequence? An answer to that, what is a sequence? That's just what we have done now. What is a sequence right there? Now, let's talk about types of sequences. Types of sequences. Okay. So the first type of sequence which you are going to see is what we call the arithmetic sequence. Arithmetic sequence. And talking about the arithmetic sequence, right? Um, an arithmetic sequence, an arithmetic sequence is a sequence, all right, in which the difference between consecutive terms, the difference between consecutive terms is constant. Okay. This difference is called common difference. Common difference. And it is usually represented by small letter d. Okay. That's the common difference. Okay. So it can be called an arithmetic sequence or an arithmetic progression, right? So uh in an arithmetic sequence, in an arithmetic sequence, all right, we have constant. Should I say constant now? We have okay, yeah, we have continuous continuous addition, addition or subtraction, continuous addition or subtraction of the, we have continuous addition or subtraction of the common difference, okay? Of the common difference. So in this case, can we then see some examples? So examples, since we already know it's about common difference, a constant addition or subtraction of the common difference. In this case, let's imagine we have 2, 5, 8, 11, 14, 17, 2, 5, 8, 11, 14, 17. Okay, and so on and so forth. All right. So in this case now, it's clear that the common difference is 3. Okay, so this involves continuous addition, continuous addition of 3. So it means, so this implies that D is equal to 3 in this case. All right. Now, let's take another example. Imagine another example that we have, say, okay, so say we have 3. All right. We have 3. Okay, let me say we have 97, and then 92, and then 87, and then 82, and then 77, and then 72, and that goes on like that. So here we have, the common difference. So the common difference that you actually see is, uh, this is equal to 5 minus 2, or 8 minus 5, or 11 minus 8. Anyhow you do it, you get that result. So here too, the common difference would be 92 minus 97, and that is minus 5. Or you can do any pair, just pick any pair. So here it's 77 minus 82. So you have to pick the number before and subtract from the number, and the number ahead minus the number before. So that's minus 5. So here, the common difference here is minus 5. So this is continuous addition of 5. So we have, continuous subtraction rather, continuous subtraction, okay, of 5. And continuous subtraction of 5 will give us a negative common difference of 5. That's minus 5 actually. Okay. So before we move on, let's talk about the formula for an arithmetic sequence. What is the formula for an arithmetic sequence? Of course, we're still going to do we're still going to talk about it better later. So talking about the formula, right? So okay. Now, using the first example, we can use any of the examples to establish the formula. So you see, you have 2, all right? And then from the first example, you have 2, which call that to the first term. That's A1 is the first term. Then you have A2 to be 5 from the first example. A2 is 5. A3 is 8. Then A4 is 11, A5 is 14. Now, what do we notice here? This is 2, right? And then this is 2 plus 3, all right? This is simply 2. This is 2 plus 3. Now, this is 2 plus 3, all right? Plus another 3, okay? This is 2 plus 3 plus 3 plus 3, okay? And this is 2 plus 3 plus 3 plus 3 plus 3. So see the pattern now. This is more like so there's no 3 here, right? So at the end of the day, this is like 2 plus 3 in one place. This is 2 plus 3 in two places. This is 2 plus 3 in three places. And this is 2 plus 3 in four places. And it goes on like that. So we can actually say this is actually 2 plus 3 in 0 place. Okay. So what does this tell us? It means that if we continue and we move as far as an, it means that the nth term, or the last term, so to speak, is going to be something like, so you can see, okay, we can even take it further and say this is like, okay, this is like 2 plus 3 multiplied by 1 minus 1. Okay, you see this is 1 here, and this is 2 plus 3 multiplied by 2 minus 1. You see this 2 here, and this is 2 plus 3 into 3 minus 1. This is 2 plus 3 into 4 minus 1. And this is 2 plus 3 into 5 minus 1. So if we go to n, right, it simply means we're going to have 2 plus 3 into n minus 1. So what does that tell us? Knowing that this is A1, this is the first term, and knowing that this is the common difference, it simply means that, it simply means that the So we can say, therefore, the nth term of an, yeah, we can even complete this, right? So this simply means we have the first term plus the common difference multiplied by n minus 1, which is the same thing as a1 plus n minus 1 times the common difference, okay? So we can say, therefore, the nth term of an arithmetic sequence, the nth term of an arithmetic sequence is given us an equals first term a1 plus n minus 1 multiplied by the common difference. So this becomes a very powerful formula. So if you need the nth term of an arithmetic sequence, this is what you have, okay? So, but I mean, we're still going to have a whole video dedicated to arithmetic sequence. So let's wait for that till we get it. But this is basically how to arrive at the formula. Of course, just like we already know, this is the nth term. This is the nth term. This is the first term. Okay. This is the uh number of terms. Number of terms. And of course, D is the common difference. The common difference. Like that. So that's an arithmetic progression. That's how that goes. All right. So let's move on to talk about the the next important sequence, if you like, and that is the geometric sequence. Geometric sequence number 2. Okay. Yeah. So let's talk about the geometric sequence. Okay. So for the geometric sequence, it's clear. Yeah, I mean, we should know that a geometric sequence is a sequence in which each term is found by multiplying the previous term by a constant ratio, r, and that is called the common ratio. Okay, so okay, that goes. And then we can easily see, just like in the case of arithmetic sequence, right? I said it's about, in an arithmetic sequence, we have continuous addition or subtraction. So when you say multiplying, right, it could be multiplying by a fraction or by a whole number. So in that case, we can see it as that in a geometric sequence, sequence, I want to make it correspond with this. Okay, we have continuous. Yeah, in a geometric sequence, we have continuous multiplication, or division by the common ratio, So in that case, we can talk about some examples. So let's see examples. So imagine that you have, say, uh, let's even take the simplest, one of the simplest you can have as 1, 2, 4, 8, 16, 32, 64, and so on and so forth, right? So this is a very good example. What is happening here? So here now you see that to get the common ratio here, you have to do something like this. This is 2 divided by 1, or it's the same if you say 8 divided by 4. You go ahead and come back, then, or whatever, even 64 divided by 32. So you see that the common ratio here is 2. So here we have constant, or rather continuous multiplication by 2. continuous multiplication by 2. So that's why 2 is the common ratio. So we can have another example. Say we have, imagine that we have 3, 4, 3, and then we have um okay, 3, 9, 27, 81, 243. Yeah, it's 243. So we have 243, we have 81, we have we have 27. Okay, we have 27, we have 9, we have 3, we have 1 over 3, we have 1 over, say, 1 over 9, and so on and so forth. So what's happening here? The common ratio here would be 81 over 243. Okay, and that is the same as 9 over 27. Oh, okay. I think I jumped something here. The next thing after 3 actually should be 1, and then we have 1 over 3. So we have 1 over 9. And so, I mean, if we are taking it's 1 over 243, 27, 9 over 27, any consecutive pairs will give you the same thing. So the easiest will be 1 over 3. So you see, all of this is 1 over 3. So we have here continuous continuous division, continuous division by 3, okay, which corresponds with continuous division by 3. You know, that corresponds with multiplication, continuous multiplication, continuous multiplication by 1 over 3. That's basically the idea here. So now, how do we obtain the formula in this situation? So let's talk about the formula here. And I'm going to use the first one like I did the other time. So to get the formula, right, you have 1, 2, 4, 8, and all that. So imagine you have 1, you have 2, you have 4, you have 8, you have 16. Let's even stop here. You know, this is 1, and then this is 2, this is 2, okay, and then, okay, just like we did before, right? This is 1 times 2, and this is 1 times 2 times 2, right? This is 1 times 2 times 2 times 2. And this is 1 times 2 times 2 times 2 times 2. So naturally, this is A1, A2, A3, A4, and A5. Okay. So this means we have this is like 1 times 2 raised to power 0. This is 1 times 2 raised to power 1. This is 1 times 2 raised to power 2. This is 1 times 2 raised to power 3. And this is 1 times 2 raised to power 4. And what is happening here? That simply means we have the first term multiplied by the common ratio. You know, we have constant multiplication by 2. So we have the common ratio, which is equal to 1 minus 1. Okay, because 1 minus 1 is 0. So this is 1 times 2 raised to power 2 minus 1. This is 1 times 2 raised to power 3 minus 1. This is 1 times 2 raised to power 4. Okay, so this 4 here now, you see, minus 1, just like 3 minus 1, 2 minus 1, 1 minus 1. And here you have 1 times 2 raised to power 5 minus 1. So what do we see? So if we take it all the way down to n, so it means we are going to have we are going to have the first term, right? We are going to have, okay, let me just write what we can have. So we have 1 times 2 raised to power n minus 1. So that means that this is the same thing as the first term, A1, times the common ratio R into n minus 1. So can we conclude then that the formula for arithmetic geometric sequence, okay? So therefore, the nth term of a geometric sequence, the nth term of a geometric sequence is expressed or can be obtained using this expression that an is equal to a1 times r raised to power n minus 1. So this is the formula for geometric sequence. So this is the nth term, because this is the first term. This is the common ratio, the common ratio, and n common ratio. This is the number of terms, number of terms, like that. All right, so those are like very two key important types of sequences. So can we see other types of sequences? That's number three now. Other types of sequences. I mean, you can make up your own sequence, right? But just follow a pattern, just be able to have a pattern around it. Okay. So other types of sequences, right? We have a popular sequence called the Fibonacci sequence. Fibonacci sequence. I think we're still going to talk about this a bit more later in other uh videos, okay? In another video, maybe. So in the Fibonacci sequence, right, each term is the sum. Each term is of the sum of the two preceding ones, okay? So there's definitely, you can actually put a pattern to every sequence. So in the case of Fibonacci sequence, right, each term is the sum of the two preceding ones. So you need two starters, or better still, you should understand here that you can start with 0 and 1. Starting, okay, I guess let me just put all of that together. So each term is the sum of the preceding two terms, starting with 0 and 1. Okay. Starting with starting with 0 and 1. So a Fibonacci sequence is simply this. I mean, you cannot make it up, like it's just what you have. Generally. So you have 0, 1. If you start with 0, 1, so to get the next term, you have to add 0 and 1. So that's 0 plus 1, of course, is 1. So the next term is 1. Then 1 plus 1 is 2. So the next term is 2. 1 plus 2 is 3. So the next term is 3. 2 plus 3 is 5. So the next term is 5. 3 plus 5 is 8. So the next term is 8. 5 plus 8 is 13. So the next term is 13. Then 13, 8 plus 13 is 21, I believe. So the next one is 21, and so on and so forth. So that is what your Fibonacci sequence looks like. It will interest you to know that this Fibonacci sequence actually has some implications in biology and features in plants and even humans, right? I think it has a connection with beauty in women, or I mean human beings generally, I think. So we'll explore that as we move on later. So let's go on to another type of sequence called the harmonic sequence. Harmonic sequence. So for harmonic sequence, the harmonic sequence is actually the reciprocals um, of the natural numbers. Interesting. The reciprocals of the natural numbers. That's the harmonic sequence. Okay. So, and that's just straight to the point. So the natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, right? So the harmonic sequence is something like 1 over 1, then 1 over 2, 1 over 3, 1 over 4, 1 over 5, and on till you get to say 1 over n, anywhere you want to go to. So those are like two other types of sequence. There are many more we can explore, but let's stop with these two for now. So next thing, let's talk about notation and examples. Okay, well, maybe examples may not be necessary, just notation basically, and we'll be good to go. All right, so let's talk about notation of sequences. Notation. Notation of sequences. That simply talks about how you can represent sequences. Um, so a sequence is A sequence is often written as this. So you have a collection of all ANs, right? Where N is the index, N is the index or position, N is the index or position of the terms. Okay. So for example, in the arithmetic sequence, in the arithmetic sequence 2, 5, 8, 11, and so on, the sequence is written, as, say, AN equals 2, 5, 8, 11, and so on and so forth. So of course, this is A1, this is A2, this is A3, this is A4, and so on and so forth. All right. So generally speaking, generally, a sequence, can be expressed, as this AN, and that leads to A1, A2, A3, A4, and so on and so forth. So that is the notation. So uh, just like we have found before, right? We can also talk about the general term of a sequence, right? General term of a sequence. So here we are basically talking, so the general term, right? The general term, which is also known as the formula, the general term or the formula of a sequence allows you to find any term, in the sequence, okay, in the sequence without listing all the terms, Okay, so you can see that, for example, right? For example, in the arithmetic sequence, which is 3, 7, 11, 15, it is clear that here, uh, in the arithmetic sequence 3, 7, 11, 15, the first term, the first term, A1 is 3, for instance, and the first term A1 is 3. The common difference, D is equal to, say, 7 minus 3, or if you like, 11 minus 7, and all of that is 4, such that the general term, is AN equals first term, that's A1, um plus the common ratio, that's 4, into okay, I mean, since it's an arithmetic sequence, we already know it's AN is equal to first term plus N minus 1 multiplied by D. So for this one now, so it's basically AN equals first term 3 plus N minus 1 times the common difference D, which is 4. So this is the general term for that particular one. Okay, so that goes. Now let's complete this by talking about visualization. Can we visualize sequences? Visualizing sequences. Visualizing sequences. So sequences. Sequences can be visualized using graphs. Okay. Sequence can be visualized using graphs where the horizontal axis, represents the term number n, and the vertical axis and the vertical axis represents the value of the term, of the term, the value of the term, which is an. All right. So we see that for an arithmetic sequence, the graph will be straight. Okay. The graph will be straight, or will be a straight line. The graph will be a straight line since the terms increase by a constant value. Okay. Then we also have that for a geometric sequence, the graph will show exponential growth or decay, depending on whether you are multiplying or dividing. So decay if the common ratio is a fraction. If the common ratio is actually between, if the ratio is between 0 and 1. Okay. All right. So can we just demonstrate that with what I gave the other time? So imagine that you have we have, okay, let's take examples, right? Examples. Imagine what I gave the other time, that we have an AP for an arithmetic. Okay, let me just do this. So we have the arithmetic sequence AN, which is equal to 2, 5, 8, 11, 14, 17. The next will be 20, 3, 8, 5, 8, 11, 14, 17, 20, and so on and so forth. Okay. So what we are saying is that on the x-axis, so we can have the graph will just be something like this. So we have 1 on the x-axis, 2 on the y. So first term, second term, third term, fourth term, fifth term, sixth term, seventh term, and so on and so forth. So if we need to plot that, so we just have a graph. So we have this graph now. So here we have the number of terms, right? We have the number of terms, and here we have the actual value. Okay. So that means that, we have 1 to 7. So we can just say 2, 4, 6, 8. So that means the first term which is 1. Okay, then here we can also have 5. Or can we have 2 also? So we have 2, 4, 6. Okay, that'll be too much. Let's just do 5s. So we have 5, 10, 15, and 20. 5, 10, 15, 20. And this is 0 right here. So the first term is 2. So first term, that's 1. And this is 2. So we have this point. The second term is 5. Okay, so this is it. The third term is 8. So this is something around here. The fourth term is 11. Fourth term is 11, something close to this. The fifth term is 14. Fifth term is 14, something around here. The sixth term is 17. Sixth term is 17, something around here. Seventh term is 20. Okay. Seventh term is 20. This is this. So we can just join the line. So it is supposed to be a straight line. Never mind that it's looking a bit wobbly. So it should be perfect, right? So it should be a perfect straight line. So if we do an AP, if we do a geometric sequence, it is going to be something increasing like that. I don't know. Do we have time for that? Yeah, I mean you can do the same for GP and you see that it will grow exponentially just as expected. So let's stop here for this and we'll continue in the next video to focus on arithmetic progression in particular. I think I should take the pain for a GP. So let's do GP. All right. So given AN equals 1, 2, 4, 1, 2, 4, 8, 16. Then the next thing after this is 1, 2, 4, 8, 16. Okay, let me just stop here so that we don't also go beyond 20. So if we have this, again, the graph is going to be, of course, we are going to have this against, so just like what we had here, right? This is actually the n, okay? The number of terms, the number of terms is this. So here also, the number of terms will be 1, 2, 3, 4, 5, and so on. Okay, so we can now plot the graph. So here we have 5 terms. So we can say 1, 2, 3, 4, and 5. And this is the origin. And then, of course, this is n here, and this is an. So on this axis, we have up to 16. So we can just do 2, 4, 6, 8, 10, 12, 14, and 16. Now we can even go, yeah, we can just stop there. So 1 against 2. So we have 1 against 2. We have 2 against 4. We have 3 against 8. Okay. We have 4 against 16. 4 against 16. So that moves quickly, not the straight line thing we saw. So you see that growing exponentially. And that's how that goes. So if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Don't forget to comment. Let me know how helpful these videos are. And also let me know if there's a topic you like me to teach or a problem you like me to solve in any aspect of maths. And then like and share so that more people can have access to this great learning. So like come your way again. Keep crunching mathematics. Bye.